on Tuesday, and that is optical rotation. So we'll cover that real quickly today, and then we'll move into the next section. So after optical rotation, anything we cover today will not be on the exam. It will be on the next exam, okay? So if you remember, we really started all the way from the basics, right? So one of the things you will have to do is to convert different structures, all right? So if we give a condensed formula, right, you'll need to be able to turn that into Lewis dot structures, right, and be able to recognize those. You'll need to be able to turn that into a line structure. You know, with the Lewis structure there. You should also be able to think about the perspective drawings. Something like this, so understand the wedge and the dash system for drawing molecules. We need to be able to do a simple, or not always simple, but straightforward nomenclature. Okay. And for free response, I will take partial answers, right? For multiple choice, it's either right or wrong, but need to know your straightforward, need to know your common side groups. So isopropyl, T-butyl, isobutyl, so forth. Should also be able to name those as systematic IUPAC. We did do some practice on some alkenes. Simple alkenes, you're probably not going to see any advanced alkenes right away. Okay. We didn't get into the Z and E naming system for alkenes. We'll wait till we get to alkenes to actually talk about those. Yes, sir. You had a question? You need to be able to recognize and be able to name both. So the question might be, what is the common or accepted IUPAC, right? That would be the isopropyl. If it says systematic IUPAC, then that would be the 1-methyl-ethyl, right? Both of those are IUPAC. One is accepted or referred to as common. The other one is fully systematic or fully systematic. Okay, questions? Okay. While we're here, you also are going to need to be able to do RNS. I don't know why I froze there. So 2-chlorobutane, and we'll be able to need to be able to name this, right? So we have 1, 2, 3. My lowest priority is back, so I'm going in the clockwise direction, so that is R. So this would be R2-chlorobutane. Okay, so you do need to know your R's. The other nomenclature that we're going to be doing quite a bit now is cis and trans, so this would be trans. All right. This would be cis. Okay. We haven't covered E and Z on alkene nomenclature, so we'll get to that at alkenes. And if I just said E and Z and it freaked you out, don't worry about it. It's not on this test. We'll name it later. E and Z is like RNS for double bonds. Okay. You also need to know your hybridizations. And the things that go along with that. So we bond length, geometry, shape, and geometry and shape are slightly different things, right? Geometry is the geometry of the hybridization, where the shape is where the atoms are in space, right? So the geometry for water is still, that's an sp3 oxygen, it is still going to be tetrahedral. Right? But the shape is bent. Okay. So if it says geometry or shape, right, those are two different things. They can give two different answers. If that had been carbon, they both would have been tetrahedral. If it had been a nitrogen, it would have been tetrahedral and trigonal planar. You should be able to identify, sigma and pi bonds. You should be able to draw, it doesn't have to be pretty, it just has to be clear. Orbitals. We should be able to draw Newman projections. Okay. The learning objectives talks a little bit about Fisher projections, and so does the book. We didn't cover Fisher projections right now. I'm hoping we'll get to it later in the semester, but we were starting slow, and it was one of those things where we can pick that up later, or you'll see it in organic too. So I pushed Fisher projections back a little bit. Newman projections, yes. The other reason to do it is that if you try to put Fisher projections and perspective projections at the same time on the same test in the same day, it gets really confusing because both of them are different perspectives of looking at three-dimensional molecules, and wedge and dash is a hell of a lot easier than thinking about Fisher. You have to do more mental gymnastics to understand Fisher projections. So we'll get to them later. We hopefully will have time at the end of the semester. Okay. Chairs, right? So we should be able to draw a chair, should be able to put the largest group in the equatorial position, should be able to understand, axial and equatorial, stability, should be able to flip. When you're looking at conformations, okay, not only you need to do it, but you need to understand the energy. You need to be able to identify anti, gauche, staggered, eclipsed, right? And should be able to identify the most stable. I knew I was forgetting something. It's intramolecular forces. Helps if I spell the words right. Okay, so you should be able to identify those, especially if we're thinking about dipole. You should be able to draw a dipole moment, right? You should be able to recognize that the overall molecule has a dipole. We had a molecule like this. You should be able to draw all the bond dipoles, right? And recognize that this one would not have a dipole as shown by mu equals 0. So the molecule doesn't have dipole even though the bonds are polar. Should be able to consider boiling points. And that's closely related to melting points. You almost don't see it asked as melting points, but should be the same. One we didn't talk a lot about in class, but there was some homework on it, is solubility. Solubility is going to be based on what type of intermolecular interactions are going. So if it's hydrogen bonding, you have something that's hydrogen bonding, it's going to be soluble. If you have something that's polar, it's going to be soluble and polar. So really that's recognizing what is the polarity of the solvent they're asking about. If they say, is this, which of the ones would be the most soluble? So let's take a question. Which is most soluble in hexane? And we give right, where first we need to, first thing we should do is actually think about hexane, right? And what is the intermolecular forces for hexane? Does it have an ion? No, so it's not ionic. Does it have a hydrogen bonding atom? No, it's got hydrogens, but no hydrogen bonding atoms. Does it have a heteroatom that would cause a dipole? No, it's all carbons and hydrogens. So this one is going to be van der Waals. So if we look down here, then we do the same thing, right? Got to look at your solvent first and then look down here. Does this have an ion, the first one? Yes, that sodium is going to be positive, right? That means the oxygen is negative. Again, lithium, sodium, potassium. If you see those are positive. Whatever's next to it is negative. Okay, so this is going to be ionic. Here I have a hydrogen bonding hydrogen, so that's hydrogen bonding. And then here I have a dipole moment. So this is dipole. So if we looked at which is the most soluble in hexane, it's going to be the one with characteristics most like hexane. So that means this is going to be the most. And if we looked at it, it would be like this, where potentially that ionic compound wouldn't even be soluble in hexane. Ethanol, you'd probably get a little bit of it go to hexane, especially if you stirred it up really hard, you know, and it was 100% hexane and not, you know, 95% ethanol. But then the chloroethane here would dissolve no problem, be totally miscible. You wouldn't notice it was there. Okay. So that's how solubility. I didn't give you any problems like that in class, but there were problems on your homework, and that goes back to like versus like, and most of you have been dealing with that since high school, if not elementary school. I had a great 4th grade teacher, and we did it back then. I also had a great 8th grade teacher that we finished the biology book, so we just started naming organic molecules. He thought it was fun, so you know, maybe that's why I'm an organic chemist, because my 8th grade, you know, football coach, biology teacher decided that, hey, we're finished the books, let's learn nomenclature. And so we named organic molecules for a whole month. So, hey, fun, right? That's what y'all do when you're at parties, draw things down and try and name them. Yeah, okay. Although you're not supposed to be at any parties right now, so all virtual. Okay, questions about what could be on the test, or what other things about the test? Yes, sir. I call it it's I think it's formerly called the perspective drawing, but I usually call it the wedge and dash just to make it very, very clear. It represents a 3D perspective, so I think that's the term. I've always just called it wedge and dash because it's easier to remember that way. Yes, ma'am. Oh, yes, resonance. Good question. Yeah, you will be able to need to recognize resonance. You will need to know conjugation, right? So if we looked at this molecule, right, we should be able to show the resonance structure for that. But you should also be able to recognize that because there's an sp3 carbon here, that this is not conjugated. So understand what conjugated, non-conjugated is, isolated double bonds versus conjugated double bonds, and then be able to draw the resonance structures. And then again, you always go from high energy to low energy. So if you're going to a positive, you move towards the positive. If you're a negative, you go away from the negative to move your electrons. And this would be both of the resonance contributors for this compound. Good question. I forgot about that one. Other questions? Yes. You know, the aromatic, when we go to aromatic, you have the Huckel's law, right? So you have the 4n plus 2 pi electrons, planar, continuous pi system. So at this point, you should be able to recognize simple aromatics. At this point, I'm not going to ask any more difficult aromatics. So your online homework had some pretty complex ones. At this point, they're going to be pretty straightforward. But you should be able to recognize this, right? So 4n plus 2 pi electrons means that you have 2 electrons, 6 electrons, right, 10 electrons, so forth. Planar, right? If it's not planar, it's not going to be a continuous pi system because once you go out of a planar, right? If we went to this, an orthogonal, then you're not going to have any overlap. So it has to be planar for that overlap. Positive charges can help with I have a hard time drawing sevens. That 7, 1, 2, 3, 4, 5, 6, 7. Yeah. So if we look here, right, we could put a carbocation right there. The carbocation is sp2, which means that it has a p orbital, which means I have a continuous p orbital system through this ring. And because it's positive and not negative, I still only have 6 pi electrons, right? So this could be aromatic. So you should be able to do some of the simple ones. The book had some pretty complex ones there. I mean, the book and the online homework had some complex ones. We're going to get back to aromatics and we'll do the complex ones when we get there. At this point, you should be able to recognize these things. Yes. Huckel's rule? Yeah. So Huckel's rule is a 4n pi plus 2. So you need all of these things to be in place for aromaticity. Okay. Again, I'll send out the learning objectives so that you'll see specifically which ones that we will cover and which ones we won't. As far as the book versus the online homework, I've gotten that several times. Go with the online homework. If we didn't cover something in the book, the one thing that we'll have to look at is optical rotations. We're going to do that in just a second. But, you know, I don't think you had any optical rotation problems in the book. So we'll look at that real quick. It's pretty straightforward. We're not going to get into it in depth um, at this point. Other questions? Let me see if there's anything. Okay. So when we look at enantiomers, right, they are non-superimposable mirror images. Right, and if they were superimposable, they would be the same molecule, right? So they're not superimposable mirror images of each other. As far as their physical properties, they're almost all the same, right? So if we look at the boiling point, solubility, right, melting point, we'll get to this later, but IR and NMR, and that's one of the things you should know. The book goes right into NMR and IR right now. You'll actually get that if you take the lab. So we'll be skipping over the next two chapters and moving into reactivity. All of these things are the same. The one that's not going to be the same is the optical activity. And that has to deal with polarized light. So if we think about light, right, so we have light over here. We've got a little light source. And then we have a polarizer. I'm going to show, you can't see this in a polarizer, they're really small. But what we have over here is we have all kind of wavelengths going in all kind of directions, right? And these directions and that direction, right? And when it comes through, all of those wavelengths of light all have to be going in the same direction. Okay. So it aligns all of those. If we then take that and put it through our sample, and let's say that it was all S2-butanol, it's going to rotate, and it's hard to show this. I'll show it this way, right? It'll rotate that light. So that if I have another polarizer over here, I'm going to have to actually rotate that polarizer some degree, right? So that I can still see that light. So polarizers, if you have polarized sunglasses, this is an easy thing to do. Or if you have two sets of polarized sunglasses, or if you have a broken pair of polarized sunglasses, take the sunglasses and then rotate them around each other. And what you'll see is there'll be a position where you see through the two glasses, right? But there's also going to be a position where you see none. That's because the two polarizers are now opposite, right? So this one is only letting waves to come through this way, but this one is now only letting waves go through the other direction, right? So one's going vertical, the other one's going horizontal. What happens when you have a chiral molecule that is purely chiral, all we have in this case, right, is S2-butanol, is that you get a slight rotation. So you polarize the light, so the only wavelengths are the wavelengths that are going vertical, and then when it passes through that sample, they get diverted, either to the left or to the right, either positive or negative, a certain degree. okay? And then you read that by taking another polarizer, right, and rotating until you get the best intensity of light, right? Meaning, so if you think about it, I've lined everything up and then it gets bent. So that means my polarizer over here, I need to rotate to where it lines up with that so that I get the highest light intensity. So that's optical activity, right? So we're looking for the optical rotation and the optical activity of these chiral molecules. This is different between enantiomers, okay? If we think about diastereomers have different physical properties, right? They can have slightly different boiling points. They can have slightly different behaviors, right? But in enantiomers, everything's the same except this optical activity, the way they interact. And if we think about, you know, if we had perfect hands, right? If we were a hand model, right? We could think about it that everything should be the same with our hands, but the way they interact, the way they hold a cup, the way they hold, like we just bought my daughter left-handed scissors, right? So the way they hold scissors that are made for either right or left-handed is different, right? But you have to have something that's chiral to interact with it, but also just optically, right? So the optical rotation, the difference, there's an optical difference between our hands, but every other, if we had perfect hand model hands, what was that silly show where they had the hand model? I can't remember. It was not a good show. Don't worry about it. So if we look here, right, we get to the, we get this optical rotation. So if, let's say, and I'm going to make this up because I can't remember the number. I think it was 15, but it might be 27. Okay. So if S-butanol rotated light positive 15 degrees, then R2-butanol would rotate light minus 15 degrees. So the enantiomer has the opposite optical rotation. If I had a mixture of 50% S-butanol, 2-butanol, and again, I'm making up the 15%, so if you go look it up in a book, it's not fake news, it's just, I'm just picking a number off the top of my head. Okay. Now, if I had a mixture of this, right, so if this is 100% S and 100% R, then if I had a 50-50, what would be my optical rotation? 0 degrees, right? So what you can do is use the optical rotation of a sample to determine the purity of the molecules, right? And so I can determine if a molecule is going to be all S if it matches the determined percentage, but I can also tell if a sample is 25% S and 75%, right? Because 25 and 75, what would be the difference? Well, what's the difference between 25 and 75? Well, it'd be 50%, right? So therefore, whatever the value was, so let's say it was 15%, right? I would get 7.5. And it would be negative, right? Because my R is negative. So optical activity can give me the ratio of enantiomers in a solution. It can tell, it can verify is it positive. Now, this is very important biologically. There was a drug that was used for morning sickness, this the thalidomide. Thalidomide was an enantiomer. They had two different enantiomers. It turns out that one enantiomer worked perfectly fine for morning sickness and had really no side effects. The other enantiomer had horrible side effects. And that other enantiomer, and depending on the maker of the compound, it turns out that there was slight differences. But the other enantiomer, this was shown as a racemic mixture. So this is known as racemic, meaning that it's 50% one enantiomer and 50 other. Turns out that there was a group of children known as thalidomide babies because their limbs weren't fully developed. So tendencies were shorter forearms, hands at the elbow, same thing with feet, sometimes feet at the knees, or really, really short arms. And this was from this morning sickness drug where one enantiomer was fine, the other one's not. So now in the US, whenever you have an optically active molecule, meaning you have a chiral center, and almost all drugs are, you have to make a pure S and a pure R, so a pure one enantiomer and a pure other enantiomer, and you have to test those independently to see if the results are the same. Now, in most cases, right, since almost all of our structures in our body are chiral, they won't be the same. But what you have to prove is that one works and the other one does absolutely nothing, right? Or you have to only sell one enantiomer, right? So you can't sell racemic mixtures of drugs unless you can prove that the enantiomer that doesn't work doesn't do anything at all. If it does anything, especially negative, right, then you have to sell it as a pure enantiomer, right? So creating pure molecules has been an important organic structure for a while. So this is optical rotation, right? So what kind of questions would you see on optical rotation? One, that there is optical rotation, right? To understand that different enantiomers have opposing optical rotation. So if it's one enantiomer or another, that diastereomers have all kinds of different physical properties, right? So a diastereomer having an optical rotation versus two diastereomers, they could have, one could be 27 positive, the other one could be 15 positive, right? There is not that same interaction that you see with enantiomers, the mirror images. You should be able to understand, right, that a racemic mixture has zero, right? So whenever you get a racemic mixture, that means you have zero optical activity. Even though the mixture has optically active molecules in there, it has a 50-50 mixture of those optically active molecules, right? And then you should be able to understand this calculation, right? That you're going to get somewhere between the pure rate and zero anytime I have a mixture, and that percentage is going to be based on the percentage of the molecules in there, right? How much of the R and how much of the S do I have in that solution? So you should be able to understand that type of calculation. Okay, not a big area, that's why it's not in the online homework, but it is important for you to understand these, and it will come up later in the year, and you'll see it when you get to biochemistry later on. Okay. All right, questions about optical activity and optical rotation. Okay, so that was exam one. Let's go ahead and start progressing into the no material. So from that line down, what we cover today will be things that will be on the next test, right? We'll post some homework on it after the test, so you won't have to worry about it. Remember that the online homework is due 8 o'clock Monday. I haven't set up office hours on Monday, but I'm going to try to, even if it's maybe a Monday night. Okay, I've got a lot of meetings on Mondays, but I'll set one up. Okay, so exam two, what we're getting in here is organic reactions. And I think the book calls it an overview. I'll call it the basics. So we're not going to be looking in particularly at organic reactions. We're going to be looking at organic reaction mechanisms. Right, and some thermodynamics. So we've already seen reaction arrows, but it's important to understand that if we have a double barbed arrow versus a single barbed arrow, this is implying 2 electrons are being moved, and this is implying 1 electron is being moved. So if I had something like this, right? I'm moving 2 electrons in this process. I'm also saying some important things, right? I'm giving, right, these electrons, right, are being given or shared with that carbon. Right? That implies that I'm making a bond. If there already is a bond, then I might be making a double bond, right? If there is no bond, I'm making a signal bond. This one over here means that those 2 electrons are leaving, right? So this is breaking a bond. So mechanistic arrows is actually telling a story, right? And for those of you that are verbal learners, what I would say here is don't just draw it, say it, right? The electrons from the oxygen are being given to the carbon. The carbon's shared electrons with the chlorine are being given to the chlorine. That's creating a bond between the oxygen and the carbon, and that is making the chlorine negative, right? Go ahead and say it. If you are a verbal learner, verbalize this. What we're showing in pictures, right? Think about this as cave drawings, right? What I'm doing in organic chemistry drawings right here is I'm telling a story. I'm telling you what is going to be happening. Going back to the idea of the difference between 2 barbed electrons and 2 barbed arrows and 1 barbed arrows, you could have something like this, and I'll go ahead and put the electrons in here so it makes sense when we're done. And here, if I hit this with light, and that's not the important part, what we're focused on right now is just, but the OCD in me says that we have to hit that with light, right? This doesn't just spontaneously happen, right? Notice that I used this barbed arrows, which this time what I'm saying is, 1 electron is going to each side. Okay. Okay. These are radicals, right? So we end up 1 electron versus pairs of electrons or absence of electrons. So instead of ion or ionic type of molecules, we're doing radical. And again, it's saying a story. Each of the electrons are going towards one of the chlorines, right? Forming 2 radical chlorine molecules. Okay, questions about the arrow movements? We've seen some of this with resonance. So if we think about the general types of reactions, and again, we're going to be going back to these again and again. Some of these examples will be expanded in their own full chapters, in some cases 2 chapters. But in general, we have a few base types. The one you're going to see a lot is proton transfer. Okay. Also, it's a variation of an acid-base reaction. In an acid proton transfer, the thing we're transferring is a proton, right? It turns out that proton transfers are probably the most common reaction that occurs in the human body, right? Protons being transferred from one atom to another over and over and over again to get different reactivities. In almost any enzyme mechanism, there's going to be at least one proton transfer, if not 7 or 8, right? It's just that common. What happens in a proton transfer? Is that we transfer a proton. So electrons go to the proton. Electrons leave that proton. It's not going to be able to share more than 2 electrons. So the electrons here going back to the oxygen. So I made a new bond with the proton. One that occurs a lot in a biological system. Here it's not a negative, it's an amine. That amine has a lone pair and it can accept that proton. So it does. So we get a proton transfer. The carboxylic loses the proton. Now, since it was neutral, it's giving up an electron, so it's going to be positive. Plus then the carboxylic acid, the carboxylate. Questions on this one? Yes, sir. Here, left side. This one does not have a negative charge. So if we look, oh wait, good catch. I should have 2 hydrogens. Yeah. And it would have been positive, but yeah, it should have 2 hydrogens, right? NH2. So primary amine can accept a proton from an acidic proton, right? So they get a proton transfer. So we're going to see lots of proton transfers, and some of our mechanisms are going to be made up of proton transfer followed by something else followed by a proton transfer, right? So you're going to see proton transfers a lot. Whenever you hear me say it as we go through the semester, realize that this is very common process. If we look at something like this, now it's not obvious up here. We had a proton, we had an acidic hydrogen. We'll spend a lot of time on acid bases over the next couple of weeks. But in this case, it's pretty obvious. Down here, what you have to do is you have to use what you've learned about structure. Okay, the O minus tells me that that's electron rich. That's pretty straightforward, right? But then what about the other? What do we know about it? Well, I got a dipole, right? And since I have a dipole, that means I have a partially positive and partially negative. So I have a carbon that's a little bit electron deficient, and I have a chlorine with a little bit electron negative, but then again, chlorine likes to be negative, right? It's a halide. So if we're thinking about what could happen here, and here's one of the things, I'm going to show you these, but this is also the thought process you need to be thinking about. What's potential that can happen here? I've got an electron rich, I have an electron poor. What is the electron rich going to do with the electron poor? going to give its electrons. But if it gives those electrons, what has to happen for the chlorine? Well, they can't stay there anymore, so the chlorine has got to leave. So now I've made a bond, right, with that carbon, and my chlorine is left as the negative. And this all happens in one step. That's what concerted means. It's all going to happen in one step, not two steps. Okay, so electron rich going to electron poor, something leaving. What do we need to know about the thing that's leaving? Okay, it's got to be more stable than the thing that's coming in. If it's not, what happens? The chlorine comes back in and kicks back off the OH, right? Because there's still a dipole moment between the oxygen and the carbon. Which of those would be more stable? Which would you rather, and do not do this, this is just an example, would you rather stick your hand into a solution of sodium chloride or stick your hand in a solution of sodium hydroxide? Okay, would you rather swim in the ocean or would you rather swim in Drano? The ocean, right? The chlorine is pretty stable. It's happy being negative. You know, it's a halide. It's good. No problems, right? So it's stable, right? So that's one of the things that as we go through all the reactions, that's what we're going to be looking for, right? We always want to go from high energy to low energy, right? If we go from high energy, if we go from low energy to high energy, something has to be forcing it, right? Or there's something there we're not seeing. Right? Sometimes it's entropy. It's not obvious. Sometimes, especially in biological systems, you'll have some things that seem like they're going up, but within that enzyme, the enzyme makes that process endothermic, meaning that it is positive within the enzyme. But if you try to do it outside the enzyme, you're not going to get it to go. Okay. So the structure of the enzyme actually makes that go from high energy to low energy, right? The way to think about it is nature's lazy, just like us. Right? So we're not going to do many things that we don't want to do, right? Same thing with that. Luckily, we have a little bit of drive. That's why you're showing up to a 7:30 a.m. organic chemistry class, because it's delayed gratification, right? If I do good in this 7:38 organic class, then I'll move forward my career. I'll have a good life, and I'll be able to retire to Italy when I'm 60, you know, and then spend the next 30-something years drinking wine and eating great pasta. Okay. Or whatever the thing here is, right? Going on hunting trips or sailing a boat or, you know, whatever. Yes, ma'am. Mm-hmm. We're gonna go over this when we get to acid and bases, but it turns out that this proton here is actually more acidic than this proton here. Right? So ionic by itself is not going to be less stable, right? And what it has to actually do with is how dissociated is this hydrogen versus that hydrogen. It's a subtle difference, but this is actually a more stable than this. Now, that makes our brains hurt, right? Because positives usually indicate something's wrong. Negatives usually indicate something wrong, but not always. Think about sodium. Sodium doesn't mind being positive. Chlorine doesn't mind being negative, right? And so in this case, the acidity of this proton is actually less than the acidity of that proton, right? So the ability of this proton to be given away is less than the ability of that proton to getting away. And when we get to acid base, we'll look at those, right? And part of that has to do with the resonance structures in this. And it also has to do with the fact that the nitrogen doesn't mind that, you know, sharing 4 bonds versus just having a lone pair, right? The overall stability of that molecule and the behavior of that nitrogen, okay? So there is a tendency, and it's not a bad tendency, and it's not a bad way of looking at things, is that negatives and positives are good and bad. But the truth is that there's more nuance to that, right? A negative could actually be more stable than a neutral. And in this case, this if if this was in solution, and actually I can tell you right now, in your body, it's several billion of these molecules are going on, because this is amino and this is an acid. What is that? Amino acid, right? If you have amino acid in a neutral solution, this is its form. Right? It's actually the acetate and ammonium. Okay, so we'll get to that, but there's some energy differences here that aren't that obvious for some of these. Now, in other cases, it's pretty straightforward, right? Here I have a negative, here I have a negative. Which of these two negatives are more stable? This one is. So the reaction is going to go forward. We can also have a situation where we have a substitution, but the substitution is happening in steps. And this one, because of the structures, it's hard for the acetate to come in the backside, so that's not going to happen. So what happens if the bromine just leaves? Right, I end up with a carbocation. I've tried to draw it planar here because it is planar, right? And then I have my bromine negative. Now the bromine can re-react with that positive charge, right? That would just make this air go back. Or, right, I could have the electron rich react with electron poor. Right? And in this case, we have stepwise. And we'll spend a lot of time on this later on. Right? But right now, just think about these different types of processes that can be happening. Okay, so concerted, all happening in one step. We get a substitution. You know, are stepwise, taking steps to get there. If we take our first example up here, right, what's happening is the O minus is reacting with the CH3Cl, and that is going to a more stable form of the methanol and the chlorine. Okay, and it always confuses me whenever I was learning this, and still kind of does. What, you know, you want numbers, and what is a reaction coordinate? That just means what processes it is in the reaction coordinate. So what molecules are there? So if you can see here, I've started with my two compounds that I had in my substitution, and on the second one, that is where my products are, right? Now, when I do this, there's always going to be an energy of activation. It can be very small or it can be very high, but there's going to be a process where what happens in the thermodynamics is I'm actually going up and then back down. Now this energy here, right, is the energy of activation. Now that can be really small or it can be really, really high, right? But there's going to be something, because the first thing you have to have is that these two things come together. And even in ionic compounds where these things almost seem like they did snap together, right? They still have to get there. And there is a process of them coming together, right? There is, even in this one up here, there is a p orbital, right? And that oxygen negative has to find it. What happens if the negative and positive and they come like this? Well, it doesn't react, right? It has to come in the right coordination, right? So there's going to be some type of energy of activation. There's also going to be this energy change here that we can refer to as delta G. And delta G, we have to go back and look and see. So Gibbs free energy. And no, that's not an Australian boy band. But delta G is equal to delta H minus T delta S. So what's going into this is enthalpy and entropy. So enthalpy is just energy, right? Either exothermic or endothermic that's going into the reaction. Entropy is the chaos, right? That's going to be, are we increasing or decreasing the chaos? Are we going from cyclic or acyclic? Are we combining two things into one thing, right? Or are we combining two things becoming three things, right? How has the order changed, right? And notice that delta H is set without temperature, but delta S does have a temperature, right? So by changing the temperature, I can potentially change the entropy that's going into the molecule, into the delta G, but I'm not going to impact my enthalpy. So delta G gives us the overall reaction, but it has both of these parts in it, right? Delta G equals delta H minus T delta S. So for the reaction to go forward, it needs to be, delta G needs to be okay, it needs to be negative to proceed without any external interactions. And that takes in part both the delta H and the minus T delta S. So if I had a reaction that went up, if I had this example, right, I started A plus B and I went to, C plus D. Here I've got a positive delta G, right? So without external stimuli or energy, what's going to happen to this molecule? This reaction is going to revert back down. Now I can force it with an enzyme, I can force it with energy, I can force it with constructs, right? But in general, if this is just two molecules sitting out there, this is going to, I could potentially get it to go forward, but it'll go backwards faster because the delta G is in the wrong direction. If we look at our other example, we start here with our products. And what happens in the first step? Well, the first step is the bromine leaves, right, to give me this carbocation. Which of these two do you think is going to be more stable? This or this? This or that? This is going to be more stable, right? I've gone through a higher energy species. I've gone through a carbocation. How stable is that carbocation going to be? Not much, right? Why? This carbon doesn't have a octet. Right? Now, it has these different carbons, and again, we'll talk much more about this as we continue through the reactivities. These carbons can contribute to that positive, which makes this more stable than, let's say, this one up here would have been. It only had one carbon attached, but that's still a high energy species. So when I look at my energy diagram, I may not know the relative places to put the levels, but you should be able to, and you will as we continue through semester, always be able to draw the energy coordinate diagram like this. That carbocation means that that set of intermediates is going to be a higher energy species. But then as we go to this compound, and I should continue to draw the Br minus here, is there any big indication, right, that these should be less stable than those? No, right? And so potentially we could have our, oh, I wrote the wrong word. Now, if we think about our energies, it's probably going to take a decent amount of energy to get over that bond breaking, right? That bond breaking is probably going to be, you're going to high energy species anyway, so you've got a really high energy of activation. That then gets us to this middle point. This middle point is our intermediates. Now, intermediates are different than transition state. Okay, transition state is the transition between those two sets of compounds, right? And we'll look at a couple of transition states in a second. But then if we think about this and, you know, just thinking about what's going on in this reaction up here, it probably took a lot of energy to just break this bond, right? So that energy of activation being high is likely. And there's experiments we could do to actually determine these. I could do a bunch of experiments, in fact, years worth of experiments to determine what that actual energy is. But just looking at it, we should expect that to be high, right? At this point, as you continue through the semester, by the end of the semester, you should be able to look at this and go, there's going to be reactants, intermediates, products. The first step should be a higher energy step. But what about the second energy? Which, oh, crud. I didn't see it in time. I should set an alarm. Okay, so we have, so the parts of the reaction that we're looking at, right? Reactants, intermediates, products. We're almost there. For the energy of activation, if we look at the first one, we knew that was high because we're breaking a bond. We were going to a high energy species. That's going to take some energy. Oh. I should have some music I play, you know, like Boomer Sooner when you call the help desk on campus. This used to take a long time. These are what are called a laser projectors, so they can start up and cool down. Used to, it was a 7 to 9 minute process because there was actually a bulb in there that would get hot. And so it actually had to cool down to shut off. So that was a 3 to 4 minute process, and then it had to heat up before it could project, and that was a 3 or 4 minute process. So luckily we've upgraded this classroom. Okay. All right, so if we look here, then at this point, right, is that going to take a lot of energy? Would we expect that the energy of activation for this process to be really high? Moderate, low? Moderate, low, yeah. You know, so when we look at that reaction here, right, I wouldn't expect it to take much, right? And so if we look at that energy of activation, it might be higher than this, right? But it's not going to be very big. That's going to be this energy of activation. So from this, right, if we think about this, I've got 2 steps, right? Step 1 and step 2. In the previous, right, this was my example of my concerted. So in my concerted reaction, how many steps are there? Well, there's only one. It's concerted. It all happens at one time, right? This is boom, boom, done. Here I've got 2 steps, right? So I go from reactants through my transition state to my intermediates. Then I go through another transition state to my products. So step 1 and step 2. Which of these 2 steps is going to be slower? The first step or the second step? What determines that? My energy of activation, right? My energy of activation is going to determine the speed. If I add a catalyst, what does a catalyst do? Catalyst speeds up a reaction. Does it change the stability, the energy of the reactants and the energy of the products? No, it just does what? It lowers the energy of activation, right? So it can make things go faster because it lowers the energy of activation. In biological systems, enzymes are catalysts because it's lowering the energy of activation, but it's not changing the overall stability of the products and reactants. Yes, ma'am. Here, they're going to be pretty close, actually. Yeah. In this one that you're talking about, they're going to be really pretty close. And this reaction could go backwards. This is a reaction that you would actually get to work by looking at kinetics and changing. If I had a whole lot of this, right, then this is going to proceed easily. If all of a sudden I go and I put a whole bunch of this in there, I could actually probably force this reaction backwards. My energy diagram would be opposite, right? It'd be different. But you know, these 2 products are probably close, and my kinetics, my reaction mixture may actually force this one way or the other. Okay. All right, so this will give us our rate determining step. Okay, so our kinetics of this part is really going to be based around how fast this reaction goes, right? And we're almost out of time, so we'll segue into this last part, which is thermodynamic. And we'll be using these terms over and over again during the semester. So when we look at these curved arrows, and there'll be some online homework to practice, when we look at the predicting the product, so one of the things we do in organic chemistry is for predict the reactivity, right? We predict what's going to happen. There are 2 basic types of controls, and they can get convoluted, but thermodynamic control and kinetic control. Thermodynamic control really has to do with, you know, this, right? Where this is versus that, right? It's not really worried about the process of getting there. It's saying this. And if I had that big change in delta G right here, thermodynamic control, this would be the product, right? Because there's a huge delta G, this is the product. If we go over here, like she was bringing up, these 2 may not be that different in stability. So the thermodynamic product might be just slight, right? So this might be more stable than that, than this molecule, right? So potentially it could be. But if I really, really, really wanted this to go to this product, what I have to do is think about kinetic control. How do I force it to go forward? And kinetics is this process, right? So how could I do that? Well, I could change the solvent, I could change the temperature, I could change the concentrations, right? So I can change how I'm looking at the reaction and working reaction to go between thermodynamic control to kinetic. So under a certain set of conditions, my product would be the thermodynamic controlled product. Under a different set of conditions, let's say we change the concentration, maybe we went with a little bit lower temperature, then I would get kinetic control. We've never changed the time period of our class, but he comes in at least every Thursday. So, okay. All right, so we'll look at that a little bit more. Monday is the exam. I will try and get here early, so you have your whole hour and 15 minutes to take the test. If you cannot be here, so if you test positive, you need to isolate, or you do not feel well, next Tuesday, you do not have to convince me. You do not have to violate your HIPAA rights by telling me what your test results are. Just email me, right? And then I'll email you the directions on how you need to take it. If you're online right now and you do not plan to be on class, send me an email. I'll send you the directions on how we're going to do the test. Both in person and out of class, you'll have an hour and 15 minutes to do it, right? And then I will get the online homework graded, the quiz, I'll get that graded, and that'll be up hopefully today if we don't have another emergency. So, okay, yes, ma'am. Yeah. Okay, yeah. Here. It from I'm not understanding the question. So why are we getting this versus that? Other side, right? It has to do a little bit with entropy, right? And it has to do with the kinetics around the entropy. So as we add, let's say we added a bunch of bromine, I have more bromine around, so that if ever I form this intermediate, it's going to go back the other direction. Okay, so it has to do almost with chance, right? And just the concentrations of the reactants. Okay. We'll see y'all Tuesday.